So what is basically a DC circuit? What makes a DC circuit? It is a circuit where you need to have a power source, which is what we call as the EMF. When you're looking at a battery, so you have an EMF in the circuit. You have to have an external resistance or external load in a circuit. And of course, there is an internal resistance. The battery is not just a power source, it has its own resistance internally, and that's the internal resistance. So we have an external resistance, and then we have an internal resistance and the EMF. EMF is the capacity of the cell to drive electrons or to drive a current through the entire circuit. How much work a cell can do to drive a coulomb across the entire circuit. That's basically the EMF. It's energy. E stands for energy. Alright, so EMF is equal to this. Now, when you have an external resistance like that, an internal resistance, it will actually create a current. And what is that current equal to? Current is equal to the total EMF over the total resistance. Current is the total EMF over the total resistance. And in this case, I is equal to EMF over R plus R. Current I is equal to EMF over R plus R. That's the total resistance, and that's EMF. So the current is controlled by two factors. One, the external resistance that you're connecting to it. The other is the internal resistance of the battery itself. And what is making up the internal resistance of the battery? It is the resistance offered by the electrolyte between the electrodes. Whatever resistance is being offered there. So the resistance offered inside here is going to prevent a big amount of flow. So basically this is an obstruction to the flow of electric current. This is an external obstruction to the electric flow of electric current. If you cross multiply this equation, you end up getting E is equal to IR plus IR. Cross multiplying that equation, you'll get you that one. EMF is equal to IR plus IR. And this IR, I times R is the voltage drop, correct? So the EMF is equal to the external voltage drop, like how many volts is dropped here, plus the internal voltage drop. That's inside here. The external voltage drop is measured by a voltmeter connected across a resistance. Which side is higher potential? Left or right?
Left.
Left is at a higher potential and right is at lower potential. So this voltmeter is going to measure the potential difference across the external resistance. What if I put another voltmeter here? What will it read? The same thing. Good. So it is also external. It is not going to measure internal. Internal potential drop cannot be measured. You cannot measure internal potential drop. So when you connect it across here, you are technically connecting the same points. These are just connecting wires. So connecting here or connecting there is basically the same thing. So even if you connect a voltmeter right across the cell, what you're measuring is the external drop, not the internal drop. Okay? So that is the internal drop, which is lost. It's sometimes even called lost voltage because it's of no use. This thing is called lost voltage because it is of no use at all. This is the one which is actually useful to the outside. Like it can be a light bulb, it can be a fan, it can be heater, anything. This is the useful thing. And over here, that voltage is of no use. And what is this voltage made up of? Current times? Current, you can't stop it. It's the same current that's going in the circuit. But R, if you can minimize the R, then you can reduce the internal drop. Right? So the goal is, if you want to get the most efficiency from a cell, you need internal resistance to be on the lower end. So therefore, you can actually get most out of the cell. So the internal resistance is small r. That kind of controls the whole situation. watch that equation again. If I multiply this equation throughout by I, if I multiply the whole equation with I, then what happens? That equation becomes EI is equal to I square R plus I square R. So multiplying this whole equation with I, you end up getting this equation. Now, what is the product of E and I supposed to mean? Power. And power generated by the cell. So this is power generated. That's a power generated. And what is I square R? It's a power dissipated in a useful manner outside. So this is power dissipated outside, external. And internal power dissipated is the power lost internally. I'm using the term lost because it's not something that's of any use. It only heats up the battery. It heats up the battery. It won't be of any use. So the power generated is equal to power dissipated externally, which is a useful thing, plus the power lost internally. Again, to minimize the power loss, internal power loss, what you should control is this, the internal resistance. If the internal resistance is on the lower end, you get most of the cell's efficiency. To give an example, let's say you have a 12-volt battery connected to a resistance of 4 ohms and the internal resistance is 2 ohms. If the internal resistance is 2 ohms and the external resistance is 4 ohms, what is the current here? 12 divided by the total resistance, which is 6, so there's 2 amperes. So if it is 2 amperes there, what is the potential drop here? How many volts is dropped there? 8 volts. Which means if you connect a voltmeter here, it will read 8. If you connect a voltmeter here, it will read 8. Same voltage. So that's 8. Now how many volts is dropped internally? 4 volts. Out of 12 volts, you're losing 4 volts internally and 8 volts externally. So you're not getting all of it outside. It's only a limited number. Let's look at the power concept. How much power is generated by the cell? 24 what? Watt. Okay. 24 watts. 24 watts. What is the power dissipated externally? I square R. 2 square times 4, which is 16 watts. Plus the power lost internally is 2 square times 2, which is 8 watts. So you can see that energy conservation comes in there properly. 24 watts, which means 24 joules per second generated. 16 joules per second is used here. And 8 joules per second is purely going as heating the cell. It just warms up the cell. That's all it does. It is of no use. How do you minimize the loss? To minimize the loss, obviously, if you can cut down on this internal resistance, if the internal resistance is reduced, or if you take a cell whose internal resistance is low, then that solves the problem. Now, each cell has got different internal resistance, right? Each cell has different internal resistances. All right, so we have this cell. A D cell, and we have C, we have double A, we have triple A, and we have button cells and smaller ones. Okay, so these are different cells. As you can see, which one should have, I mean, if they are all new, which one should have this least internal resistance? The biggest one should have the least internal resistance. What is taking, how is the resistance, how is this one offering least resistance when this one offers more? How? What controls the resistance, internal resistance? I told you internal resistance is because of the resistance between the electrodes, because of the electrolyte in between. So how is this one? So you know the resistance is equal to rho L over A from the last chapter. So more area of, more surface area of the electrodes, you're supposed to be getting smaller internal resistance, right? So that's the idea. So this big one definitely has a small internal resistance. If it's a new cell, it may be like 1 ohm or less than 1 ohm, this one. This one, it will be somewhere between 1 and 2 internal resistance. This one could be around between 4 and 5. And this one is furthermore. So why do you use a specific type of cell for a certain purpose? Why can't you use the same thing in a different, for different applications? Let's see that part of it. And I think I mentioned this already to you last year. You know, the internal resistance, the resistance of this thing, changes due to 2 factors. One factor is age, just pure age. You don't have to use it. It's just age. You just buy it fresh because you got it on sale and just shelf it. And once you keep it there, after 3-4 years, you say, oh, I do have these cells. Okay, let me use it. It may not work. It may not work because the internal resistance has been changed due to age. And the other reason why internal resistance can change is usage. Like if you use a cell, it's going to change the internal resistance. How is age going to change the internal resistance? How is the age going to change the internal resistance? Age means like you just keep it there and you're not using it at all. The electrolyte kind of solidifies, and that solidification kind of prevents the ions from moving freely. That is what happens with the age. Okay, so you may just take a fresh pack, but 5 years old, and then try to use it in a flashlight. The flashlight is not working properly. The reason behind it is the internal resistance has gone up. 2 reasons. One, age, and the other is, that's why when you buy a cell, you always like look for the date. You don't blindly buy a cell. You have to look for the date. Now previously, they used to print the date of manufacture. They used to print the date of manufacture, which actually, I remember the times when I used to want to buy a cell, and I go and when I buy it, I'm just trying to see, oh, this was made in March 2018. Then I asked the shopkeeper, I said, do you have something made in August? I want a newer one. I don't want to take something which is made in March. If something made in August is available, I'll go for August. Why to go for something that's older? Right? So we are so sensitive to the age, and so we kind of always try to take the newest one, keeping all the old ones aside, and the old ones will never get sold. And so manufacturers now decided, okay, it's not a good idea to put date of manufacture. Instead, we'll put up to when can it last. All right? And that's why they say they print the date. It'll work up to March 2021. So you'll see March 2021. That's what you'll see. But when was it made? Was it made in 2016? Who knows? You don't know. So now what happens is, when you go and buy a cell, you're looking at only the expiry date, which is March 2020 was a long way out, so therefore it's okay. And you buy it. But then you don't really know that this was made in 2016. And they put a 5-year date. So you're actually taking something that's 2 years old already. You know what I'm saying? So we just end up buying it. that is a technique that is used these days in all the places, like milk, bread. Previously, bread used to be like the manufacturer, like when it was made. Now it is, it is done like that for, I think, the chicken, right? The broiled chickens or whatever. The chicken, they kind of tell you the time when it was grilled. So when you're actually going to buy it, you say, oh, this was done at 4 p.m. This is done at 6 p.m. I'll go for 6 p.m. 2 hours difference, but still you want the latest one, the one which is just done. And the people definitely will have problems taking the other one. And so that is why that's why they kind of reduce the price after some time. If you go to Costco, you'll see it. All of them are kind of same stuff, but on some of them, it'll reduce the price, like say 75 cents off on that. And why is it? Because it was a little earlier. So definitely there will be some difference to the product. So bread, milk, those things are, they're giving the expiry date, like best before this. And so you just look at the data and say, oh, it's long, so you can take it. Eggs, best before. When was it laid? No idea. And these days, most of these things last for much longer because they put all those preservatives and all those things. Everything contains, eggs and milk, and everything contains preservatives. They don't go bad that soon. Yeah, you can just buy those eggs and they have plenty of lifetime. But that's not the case with real eggs. If you have real chicken and real eggs, they lay the eggs, they don't last long. They start getting bad soon. Milk, fresh milk from a cow, they won't last for long because they are fresh and there is no preservative and all those things. And so that's bread the same way. Look at the bread. Sometimes I bought some bread and just left it like that, just outside, and it stays there for weeks and weeks and weeks. The expiry date is also, already crossed, and then I'm still seeing that there's nothing wrong with the bread. It's like intact. It's not changing at all. Fruits, same thing. There's an apple sitting on my desk, and that apple was there at least 3 weeks before. Yeah, I saw it on my desk 3 weeks before, and I went for the break and came back, and still that apple is sitting there, and not a single defect. It's intact. There's no damage to it. There's no, nothing from the outside. I don't see anything at all. It looks good. Again, preservatives. That's the one that keeps it going. That's why insects even won't go for it. Insects know better than us. They know if something's wrong with a certain fruit or vegetable. They won't go and eat it if there are impurities in it. But we can't tell the difference. We just go for it. All right, so anyway, internal resistance of this one is supposed to be on the lower end, but as it ages or as you start using it, its internal resistance will start changing, getting bigger and bigger. And when it becomes bigger and bigger, then what happens is the same thing cannot be used for a certain application. You can't use it for a certain application. And so that's when you say, oh, the cell is kind of dead. Well, the EMF never dies. The EMF stays intact, 1.5 always. But what actually changes is the internal resistance. Now, this one is an alkaline cell. So this one, you cannot undo the chemical reaction that is taking place there. So how is the internal resistance increasing when you use the cell? Because when you use the cell, there is an electric current inside, and that causes a deposit of some oxide on one of the electrodes. And as the oxide starts getting developed on it, the internal resistance starts increasing. Okay. Now on a rechargeable cell, the rechargeable cells normally is not a 1.5 volts, it's only 1.2. But the internal resistance is much lower than these. That's why they are most on the stronger end. You can use it for stronger applications, rechargeable cells. And when you're using a rechargeable cell, the cell is going to, it will change internal resistance. But when you recharge it, you're working the chemical reaction the other way around, and you're kind of undoing what was done. And that's why the cell kind of regains its capacity. Internal resistance drops after you charge it, and everything goes well. So rechargeable cells, your car battery is also a rechargeable one. Initially it is lead and lead oxide, the electrodes. And what is inside is a sulfuric acid, dilute sulfuric acid. Now, that is when it is fresh. When you use the car battery, the lead becomes lead sulfate, the lead oxide also becomes lead sulfate, pulling the sulfates from the sulfuric acid. That will reduce the density of the sulfuric acid. So by checking the density, you can actually figure out if the cell is to be charged or not. Okay. Now, when you recharge the car battery from lead sulfate, it changes back to lead, and this one from lead sulfate changes back to lead oxide, Pb and PbO2. And once you do that, the car battery is charged up. So it will have the voltage right, and it will have the internal resistance pretty. Now, let's take this example of 1.5 volts. I'm going to use it for a certain purpose. So if I have a cell of 1.5 volts, and I'm going to use it, let's say the internal resistance is 1 ohm. The internal resistance is 1 ohm. And I'm going to use it to light up a bulb. And I want to light up the bulb whose resistance is 2 ohms. So tell me how much is the current here? That's a light bulb, 2 ohms resistance. 0.5, 1.5 divided by 3 is 0.5. So if you have 0.5 amperes going from here, how many volts will this lamp receive? 1. So this voltmeter will indicate 1 volt, because it's 0.5 times 2, it's 1 volt. And how much is lost inside here is 0.5 volts. So the bulb is getting 1 volt. So the bulb will light up. So using this, I can have a flashlight working, because it is receiving 1 volt. But let's say you kept using it for a long time, and what happens because of usage? The internal resistance will increase. Let's say the internal resistance went up to 10 ohms. If the internal resistance went up to 10 ohms, what is the current now? 0.125? 0.125 amperes. And 0.125 amperes going through this light bulb causes how many volts? 0.25 volts. So the light bulb is going to be very dim. It's going to be very dim. It's not getting the required voltage, at least 1 volt. No, it's only 0.25 volts. So it's not going to work. It's not going to work. Oh, it may work, but you hardly see the filament. Have you seen flashlights with old batteries in it? And the filament is basically, that's it. All you see is just the filament. Or it won't glow at all. So that's what's happening here. Only 0.25 volts going to the light bulb. It is not causing enough power dissipation here. You can also check the power dissipation. What is the power dissipated here? 0.125 square times 2. How much is that? How much is the power dissipated here? 0.125 square times how much? Tell me the answer. 0.125 square is 0.0144 times 2, 0.028. 0.031. So you have 0.031 watts. 0.031 watts is very, very small. And you can see more of it is lost here than here. So 0.031 watts is very small. Is it 0.00 or 0.0? 0.0, right? Yeah. So it is a very small power dissipation, so it's not going to be working. So this cell, once it is used, its internal resistance goes up to 10 ohms and is absolutely useless. What do you do? Yeah, you throw it away because it's not something that you can recharge. So you throw it away? Yes or no?
Yeah, you can use it with something that requires less power.
Exactly. Use it for something that can use. Like for example, if I'm old enough and I'm not good to teach like 30 kids in one room because I'm old. So basically, that doesn't mean that I'm unfit. Give me one-on-one, a student, I can sit, student sits, and I can teach. No big pressure, right? So give this a smaller application. Let's say the clock. So if I'm going to use this for the clock, will the clock run? Even though this is not able to drive the light bulb, will the clock run? So let's look at it that way. So now it is 10 ohms internal resistance. And now this is the clock. The resistance of the clock is like 30 ohms. The resistance of the clock mechanism is 30 ohms. Now, will it do the work? Let's find out. What's the current? 0.375 amperes. 0.0375. And if that is going to pass through 30 ohms, how many volts is going to be here? So this times 30.
1.125.
1.12 volts. That's enough to run the clock for months. You see that? That is the so-called dead battery. But when you're taking it and connecting it to a clock, it will run the clock because you see the clock is receiving 1.12 volts. And the clock requires only a small current to work. So this current is enough for the clock to keep going. This means 37.5 milliamperes. 37.5 milliamperes, probably this requires less than that. So it will be able to work pretty efficiently, and then it will last maybe a couple of months before this is unfit for the clock. But then if it is unfit for the clock, you can still use it for maybe a wristwatch, a digital wristwatch. It'll work because it depends on resistance. So the cell doesn't die at all. It just always uses. So the internal resistance is what changes over here. This one has got internal resistance which is on the higher end to start with. So this cannot be applied. This cannot be used where this one originally is supposed to be used. So if you have a flashlight where 2 of this or 3 of this is used, I cannot just substitute that with this because this one, to begin with, it has higher internal resistance, right? This one has higher internal resistance. And the same way, this one has further higher into this one is still higher. So using these things in your calculator, because the calculator requires only a small current, so this is okay for the calculated work. Button cells are used in watches, right? The cell that is used in watches like flat, thin, it's a button cell. Its internal resistance is much higher, but to drive that digital watch, it's enough. So button cells will be, why button cells? Because more compact. That's basically the reason. So you look for compactness, you know. There are some cells which are more compact than the others. See this one? You know how many volts is this, right? 9 volts. This is a 9-volt battery. And this one? This is 12 volts. It looks pretty small, but it is 12 volts. This is what is used in your garage doors and all that stuff, the openers. And this is used in remote control systems and so on. Yeah. So this is 12 volts, and its internal resistance is high. It cannot do whatever a car battery of 12 volts can do. Okay, a car battery is also 12 volts. This is also 12 volts. But this one's internal resistance is pretty high. A car battery's internal resistance is like 0.05 ohms. Okay? Now, how can we investigate the internal resistance of a cell? How can you measure the internal resistance of a cell? Or how can you measure the EMF of a cell? Now, when you connect a voltmeter across it, what does the voltmeter read? The external drop. As soon as you connect a voltmeter, the voltmeter is taking a little current from here, right? The voltmeter is drawing a little current, which means there is an internal drop already present. The IR is already there, which means the voltmeter is only registering the external drop, which may be pretty close to the EMF, but it is not technically the EMF. So when you connect a voltmeter across any cell, it is not measuring the EMF, rather it measures only the potential drop outside. So suppose you want to investigate this cell whose EMF is E and internal resistance is R. This is a circuit that you can use to investigate. So we have an external resistance here and we have an internal resistance there. To measure the external drop, what do you need?
Current.
You need a voltmeter, right? Yeah, of course you need a current. To measure it, you need a voltmeter. So what is this voltmeter going to read? It's going to read the external drop. And to measure the current that's flowing here, you need what? Ammeter. Ammeter is a device that measures the current that's passing through itself. So the ammeter is right there, and the voltmeter is always connected in parallel to certain things. And so we have the voltmeter reading the potential difference across here. You have the ammeter reading the I. And what is the original equation? E is equal to IR plus IR, correct? And this IR, I times capital R, is this V. So the EMF is equal to V plus IR. The voltmeter measures this. The ammeter measures that. So voltmeter and ammeter readings will measure both of these. Now what will happen if the resistance is changed? If you change the resistance, then automatically this current is going to change, right? And that means this voltage will be affected, correct? Yeah. So the ammeter's reading changes, the voltmeter's reading changes. So we have this and this as our variables. Now let's make this as a subject of the equation. So V is equal to minus IR plus E. Is that right? Is that equation okay from here to here? So this is V equal to minus IR plus E. And you can see that this equation is in the format Y equal to MX plus B. So it should be a straight line between V and I. So the X variable is I. The Y variable is V. So if you plot a graph of V on the Y-axis and I on the X-axis, what kind of a graph is anticipated?
Line.
Which way? That way. Good. Because you can see the slope is minus R. This is the X variable. The slope is minus R, which means it's pointing downward. So if you really do this experiment, which probably I'll try to give you, a setup. We can experiment this and find out. So when you do this experiment, change the resistance and find out the ammeter reading and the voltmeter reading, you will get a couple of points like that. You will get points that way. And then what you do is just extrapolate those points and draw a line, straight line. The slope of the line should be what? Minus R, correct? The slope of this line will be a -1 and that will be minus R. So if the slope is coming out -2, then 2 is the internal resistance, ohms. You get it? So we can measure the internal resistance from the graph. And what about this? What's the y-intercept? E. So wherever this line is going to cut on the y-axis is actually your EMF. So the EMF of this is 1.5 volts. So if you investigate with this, you should get it hitting at the 1.5 mark. Yes, Frederick? What is this? What is the slope of this line?
Internal resistance.
Minus internal resistance. All right, pay attention, pay attention. So do you get this? This is a simple experiment that can be used to investigate and find the EMF and the internal resistance. It's a typical question that is always asked. Like, how do you determine the EMF and internal resistance of a given cell? Right, that way.
So is the area underneath that the power inside the cell?
Not exactly, because you're not having a single current here. It's a variable.
Wow.
So area is power. No, it can't be power. Power delivered externally, possible.
Yeah, I suppose.
Yeah. This is the external potential difference,
Oh, that's not.
and that is the current. So it could be the external power. Yeah. Overall external power dissipated if you're going to vary the currents from this to this. So only when the current is zero, you can get the voltmeter to read EMF. And that is technically difficult because if you connect a voltmeter, the current is not zero anymore. So the current will be something. And that's why it is never the EMF. And this voltmeter reading will become zero when you reach a certain current. The voltmeter will read zero when you reach a certain current. The external drop. Okay, so that's good. So a circuitry, a basic DC circuit is supposed to have an EMF, and you know the factors affecting the internal resistance now. And resistors in parallel and in series, we have done that last year. You can go back and check your notes. I'm just going to write down the expression. What is the resistance in series? Yeah, resistance in series is equal to R1 plus R2 plus R3. Just the sum of all the. So resistance in series is equal to sum of the resistors. Sum of all the resistors. That's basically what it is. Now that's in series. In parallel, 1 over R in parallel is equal to 1 over R1 plus 1 over R2, etc., etc. Depends on how many resistors are used. So if you sum the reciprocals of all the resistors, you will get the reciprocal of the equivalent resistance. This is this. So when you connect resistors in series, you're going to have all the resistors kind of added up. So the equivalent resistance is always greater than even the greatest one over here, right? And we've seen that last year. When you add them up, the series equivalent resistance is greater than the greatest. And when you do them in parallel, it's going to be smaller than the smallest. Do you remember doing it? Okay. Yeah.
I should have asked you earlier, but you said cells, the resistance changes due to age and usage.
Yeah.
But what about like rechargeable cells? Like, how do you?
Rechargeable cells are also rechargeable cells. Internal resistance changes by age and by usage. But the only thing is, in rechargeable cells, you can just do the reverse chemical reaction and then undo the change that is done by the usage.
Does it get rid of the resistance? Like,
Yeah, it will actually kind of get rid of the resistance. Like for example, if I have a rechargeable cell of 1.2 volts, rechargeable cells like lithium and all that. So rechargeable cells is only 1.2 volts and it has some resistance. Now if you use a rechargeable cell, its internal resistance will build up. But when you recharge it, it will come down. But it won't come down to the factory value, you know. Every time you charge a cell and recharge a cell, its life will come down gradually. A rechargeable cell has a number of cycles life. So if they say you can recharge it, charge and recharge it 1,000 times. Yeah, I mean, you're charging and recharging these cells. Once you reach the 1,000 limit and all that, it's already done. You can't do much. So if it's a fresh rechargeable cell, it'll last for much longer, just like a laptop battery. If it's a fresh laptop, the new battery in, it may last for 8 hours. And then after that, as you charge and recharge the cells, it will actually show that it is not actually holding the charge that much, right? Because the internal resistance is kind of permanently changing by age. And so it has its own lifetime. That's why, you know, after you use a laptop multiple times, the charge doesn't stay for even an hour. But then you'll be wondering, like, it used to be 8 hours, now it's only 1 hour.
So that's the same with like iPhones too.
Yeah, iPhones, they're all affected by the age. So right now my phone is not lasting as long as it used to last. Same with mine. If you have a Mac device, you can find out how many cycles it's gone through already. Check it out if you have one.
Right now.
Yeah.
Oh.
Yeah, just go to About the Mac. Click on About the Mac. Click on About the Mac, and then System Properties or something like that.
Does it do it on iPads?
It should be System Properties, and then go to Power or something like that. Resistors in series, it's simply adding them up, and resistors in parallel, you're going to do this. So if you have circuits where resistors are in series and parallel, you know how to tackle those things, right? You have done that last year again. So all you have to do is like look for the ones which are in parallel first, simplify it, and then keep simplifying the circuit until you reach the simplest circuit, and then you can start working from there.
Can we go practice one?
We can practice one of them.
Yeah.
So
This guy. Wait, isn't there like a trick you can do if you have two resistances in parallel?
yeah, shortcuts. Yeah. For two resistors in parallel, so if you have just 1 over R is equal to 1 over R1 plus 1 over R2. So the equivalent resistance R equivalent is equal to product over sum. So R1, R2 over R1 plus R2. And so that is something that you can do faster. Product over sum. So let me complete the circuitry. Yep, find the current coming out from the battery. Let's do that first. How much current is coming out from the battery? You don't require Kirchhoff's laws over here. It's just simple circuit. It's a simple circuitry. All you have to do is search for any series parallel combinations. Any parallel and series combinations, you get there. can do it in your mind actually. Just tell me how much is the current. Yeah,
Is it 2 amperes?
it is 2 amperes. I said you can just stare at it and tell the answer.
True.
It is 2 amperes. Now just focus on it more and you'll be able to see. Alright, can you see that these two are in series? So just look at the whole thing as what? 4. Can you see this and this are in series? So look at this whole thing as 12. So from here to here, there's a 12 from this side and there's a 4 from this side. Are they both in parallel? They are in parallel. This section and this section, are they both connected to the same points? Yeah. So this is connected to this in parallel. Or you can just do this, take this whole thing and fold it all the way here. Like drag this whole thing onto this side. Then you'll see that those are in parallel. Okay, so this section here of 12 and this section here of 4 are both in parallel. So use this law. Use the product over sum. So 12 times 4 over 12 plus 4, which is 3. So all this is 3. So I can just remove this. Okay, I'm doing in stages for you to understand. That is 12. And that is 4. And you can see that that and that are both in parallel. So instead of drawing it on that side, I can even draw it on this side. So once you draw it like this, the whole thing here is 3. So you're going to remove the whole thing and put 3. And now you recognize that the current is going from here, it passes through 3 and then through 2 and then through 1 and goes. So what's the total resistance? 6. What's the total EMF?
12.
And therefore it's 2. Okay, got it? So this requires just a little bit of looking at the circuit and then trying to simplify things as much as you can. So if you cannot simplify circuits, that's when you need the help of Kirchhoff's laws. Otherwise, it's okay. Now let me draw the circuit back again because I'm going to ask you further questions. What is this? 3, 5, 4. This was 3, 1. So we got to know that this current is 2 amperes. Now what's going to happen is this current of 2 amperes is going to flow here. It's going to flow through the 1 ohm. It's going to flow through this 2 ohm. So let's find out what actually has it done from this point to this point. How many volts is dropped here by the 2 amperes? How many volts dropped here? 2 times 2? 4. So 4 volts dropped here. Let me use a different color. So 4 volts dropped here. Which end is positive, which end is negative? That end is positive, this end is negative. How many volts is dropped in the internal resistance? 2 volts. Which side is positive, which one is negative? And then, what about the cell itself? Which side is positive, which side is negative? So now, between these 2 points, just find the total potential difference. The cell is making this terminal 12 volts higher. And this is killing that by 2 volts. So now it is 10 volts, right? And this is killing it by 4 more. So that means the potential difference from here to here is 6. So if I connect a voltmeter between here and here, it should read 6. It should read 6 volts between here and here. I'll explain again. This is plus 12 on this side, then minus 2 on this side, then minus 4 on this side. So overall it's going to be 6 volts. So when you say the potential difference is 6 volts from here to here, how many volts is across here? 6. If it is 6 from here to here, it's going to be 6 this way and 6 this way. So imagine you apply 6 volts to 4 ohms. How much current will go here?
1.5.
6 volts, you're connecting to 4, so it'll be 6 over 4, which is 1 point, so this is 1.5 amperes. So out of 2, 1.5 amperes runs in this direction. Now look at that side. It is 12 volts, 12 ohms, and the potential difference is 6. So how many amperes? 0.5 amperes. You can deduce that even by taking 2 minus 1.5. You could have found that out by just subtracting 2 minus 1.5. You get the same answer. But now you understood all the currents going everywhere. And therefore, if I tell you, how much will this voltmeter read? All you have to do is find out what is going on. Okay, it's 0.5 amperes going all the way here. And it's 0.5 amperes running from here to here, which will cause a potential difference of 2 volts. So from here to here, it should technically be 2 volts, if everything is right. So if in case you find that the potential difference here is not 2, it's something else, that means there is some problem with the circuitry. There's some problem, there's a defect. And the defect could be, you thought it was 5 ohms, but it's actually 50 ohms. You know, those kind of defects. So in a circuit, you know the numbers, and so you can anticipate, okay, according to these numbers, I'm supposed to get 2 volts here. And then you check with the multimeter and it does not show 2 volts. That means there is some defect in the circuit. It could be from anywhere. It could be one of these resistors is wrong. It could be the cell's EMF is wrong. It could be the cell is very old, so it's no more 1 ohm, it's like 10 ohms. You know, it could be multiple factors causing this voltage not to be 2. Yeah, so you can explore the entire circuit with the help of simple rules. If the circuit is more complicated, that's when you use Kirchhoff's laws. You should go back and find out more about Kirchhoff's laws. The first law is
0.
at a point all the currents add up. Like in the previous example, 2 amperes coming from here, 1.5 goes this way, so it has to be 0.5 going the other way. Right? That is according to Kirchhoff's first law. Kirchhoff's second law says in every closed loop, the algebraic sum of the EMFs and the potential drops should be equal to 0. That is the Kirchhoff's second law. Since we have done it in detail, go back and just review those materials and then learn. Or go to your textbook and then find out more about it. Try some questions and you'll be good. Capacitors. Now we're bringing in capacitors into circuits. So when capacitors are brought into circuits, you can have capacitors in series. Let's talk about capacitors in series. So when you have capacitors in series, what do you mean by capacitors in series? So we have a potential difference applied to capacitors such as this, that, and that, C1, C2, C3. So we have 3 capacitors connected in series. And you know what happens when a power is applied to the capacitors? The capacitors are going to charge up, correct? The capacitors are going to pick up charges. And what is this charging process? This is deficient of electrons. So electrons from here will go. And that way this terminal is going to be positive. This terminal here, and this terminal here, and this connecting wire between the two, the total charge initially was 0. But as soon as this became charged positive, what happens is this will charge itself negatively and this will automatically be positive. They just rearrange. The total charge on these 2 plates is still 0. And because of this, the same thing happens on the other side. And the negative charge comes from there. So all of them get charged. The charging current is basically the same through all of them. What is causing them to charge up is exactly the same thing. So what you understand from this is that they all acquire the same charge. They all acquire the same charge. They won't take different charges. no matter what capacitors they all will pick up only their share. I mean, one particular value. So you can write that as a point. Capacitors in series, charge will be Q, alike. All series capacitors will have the same charge. Write it down. Even though the charges are the same, the voltages are going to be different. You supplied V here, but how much will be across here? V1. How much will be across here? V2. How much will be across here? Is V3. And what's the connection between Q and C1 and V1 and all that? What's the connection between Q, C, and V? Q is equal to CV, right? So looking at this, since the voltage is V1 here and V2 here and V3 here, but the total voltage is V, so you can simply write down V is equal to V1 plus V2 plus V3. That is definitely sure. V is V1 plus V2 plus V3. Is that clear? Now what is V1 in terms of Q and C1? So I'm going to write Q over C1 plus Q over C2 plus Q over C3. You can take Q out common, so V is equal to Q 1 over C1 plus 1 over C2 plus 1 over C3. And if I bring the Q down here, divide by, so we get V over Q is equal to, V over Q is equal to 1 over C1 plus 1 over C2 plus 1 over C3. What is V over Q?
C.
What is V over Q?
C.
From the equation Q is equal to CV, what is V over Q?
1 over C.
1 over C. So this is actually 1 over C equivalent. Meaning, if I remove this whole thing and substitute it with one capacitor whose capacitance is C equivalent, it will still get the same charge Q and that voltage. So that is called the equivalent capacitance of the three of them. So what you see here is 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. And this is for capacitors in series. You see it? That is for capacitors in series. Now for capacitors in parallel, let's look at that. So this is capacitors in series. Now capacitors in parallel. Now this is capacitors in parallel. So when capacitors are connected in parallel, C1, C2, C3, how many volts is across here and across here and across here? It's all V. So V volts, V volts, V volts, they'll all get charged to the same voltage because you're connecting one voltage across all of them. And that means this capacitor is going to charge independent of this. And this capacitor is going to charge independent of this. So let the charges be Q1, Q2, and Q3. And if that is the same thing connected to the combination of this, if I remove all this and put one capacitor, that is C equivalent. So what is happening here is Q1, Q2, and Q3. So how many coulombs did this cell deliver? Q1 plus Q2 plus Q3, right? Because it's sending Q1 here and Q2 here and Q3 here. So the total charge that this is delivering is Q, such that Q is equal to Q1 plus Q2 plus Q3. And what is Q in terms of C equivalent in V? CV. C equivalent times V. What is Q1 in terms of these two? C1V. What is Q2 in terms of C2 and V? And that one is C3V. Divide throughout by V, and what do you have? C equivalent is C1 plus C2 plus C3. So in parallel, your formula is this. In series, the formula is the other one. What do you see how do you compare this with resistors?
The opposite.
Just the opposite. So if you know the resistors for sure, then all you have to think is, oh, this is capacitors, so let me just use the other one. Okay?